Okay, hi everyone. I'm going to be the chairman for this afternoon's session. And this afternoon, we're going to start with a talk from Martin Beseda, who is a postdoc working in Montpellier, and he's going to talk about the inclusion of noise environments when realizing quantum computing approach with a state average rational quantum installer. Martin, the floor is yours.
Okay, thank you very much for the introduction, and thank you for the opportunity to talk here. So first, I feel I should mention something about the title of the speech, as the very original title was something along the lines of quantum dynamics utilizing VQE in a noisy environment. But after a few preliminary results, I saw that it wouldn't be the case for today at least. So we shifted towards quantum dynamics utilizing VQE in noisy environment. But after a few runs of VQE in really noisy environment and in diverse noisy environments, I saw that it still wouldn't be the case very probably, and that we should discuss something more preliminary. So we stick with towards state average VQE in noisy environment. And that I'm saying just to mitigate your expectations since the beginning. Now, just one last point before we deep dive into my talk. Whatever way you choose to express your disappointment, do not throw tomatoes, okay? Cool. So, the outline of my speech. Like the first point I was planning to do was introducing the state average VQE approach. But I have a feeling you've already maybe heard it this week, maybe several times. So we will just skim through that. And then we start with introducing basically what is the noisy environment in a slightly more detail. And we'll introduce some basic terms so that we will basically see the danger and our opponents, we can say, in this area. It's something we cannot avoid, but which we need to deal with if we ever want to really use quantum computers in real-life applications. Then we will talk about quantum error correction. Then we will talk about quantum noise mitigation. We will describe both approaches, and we will describe basically the differences between them. And yes, then I will definitely talk about the numerical optimization, which is maybe also somehow related to the topic. So yeah, the very beginning is equation you maybe already seen, and the Hamiltonian second quantization. Considering that you've seen this several times already. We'll just have a look at the overlap integrals and the excitation operators. Also, yeah, we have the energy of the ground state with the real ground state wave function psi0, which can be approximated by the variation formula utilizing some test function which is parameterized, which is the vector theta. And when we minimize the whole formula with respect to theta parameters, we will obtain some energy which should be as close as possible, considering the limitation given by the test function character to the ground state energy. So it's always above. In the perfect case, if we literally fitted the natural wave function, it would be equal. Yeah. Here, basically, the VQE method is the quantum equivalent of MCSCF or state average MCSCF in our case. And here we can see what do we mean by the state average energy. So we simply mean the energy of all the involved states in a linear combination with the coefficients called weights being summed up to 1, obviously, and being chosen in equi-ensemble manner because of some convenient numerical properties later for the optimization. Now, this is not necessary, of course, for the method. It was just our case. Yeah. Method done in our group is state average orbital optimization VQE, where I wanted to say that basically we do not consider optimal orbital optimization in our case at all, because we do not need it for noise optimization. But what we will consider are initial circuits, which are our, let's say, starting states from which we later create the variational formula together with NZs and so on. Here we can see the Hartree state, or the representation of ground state, given by this circuit. Now, if you are kind of confused about the qubit ordering, it's because the Quiskit uses a little endian, I believe everywhere except its nature package. And also the spin orbital ordering is done in a way that, in sharp contrast with Circ, first all spin ups are ordered, then all spin downs. In contrast with Circ, where it is spin up, spin down, spin up, spin down. Okay, so we can see both the initial states. Here we can see the rotation circuit, which will be later used also in a so-called state resolution procedure. And in our case, it rotates by half. And here is on the pi, that's another convention of Quiskit. And this represents the orthogonal, basically, candidate for the first excited state. So that optimization in a state average VQE is done in a pretty straightforward way, where we apply some parameterized operator or append and NZs from the software developer point of view to our initial states. Then we assemble the whole variational formula and we minimize it with respect of the NZ parameters theta. Now, like, is this the best approximation? Yeah, it's really cool and simple and everything. And it is, but it is not the best approximation. Not necessarily for the situation of the equi-ensemble weights, where we need one additional step, which is the already mentioned state resolution, where we can take initial states and rewrite them in some sort of linear combination, we can say too, and use them as a coefficients for sine and cosine functions parameterized with some resolution and with resolution and with pi. Afterwards, we can see the situation after the application of the NZs already fitted. And we are getting into this kind of more elegant problem where we are, again, minimizing, but much simpler formula with respect to the one angle. So it's just 1D or scalar minimization, which is very convenient here. And yes, that was for the state average VQE intro. Now we are getting into something really exotic, and these are bits. Okay. So basically, what is the classical bit in a computer? Like, while the architectures themselves differ kind of dramatically, the classical bits are nowadays basically always transistors, some sort of them, and they can have the values of 0 or 1, obviously. Now, there is one important distinction, because transistors are really huge from quantum mechanics point of view. So now this is the classical question from general public, like, okay, so basically quantum mechanics do not work for them, like, why do you have like these kind of mistakes like everywhere in the computers? Basically, do we have some problems with quantum noise there? Yes, but considering the size of classical bits, it's not significant at all. Basically, this is something where we do not use its quantum properties, but it's like our big brother. It's a super heavyweight. It's resilient by itself. In sharp contrast with quantum bits, which can be represented by some trapped ions, by some photons, by some superconducting circuits. It can be a lot of things. And it's always fragile because of its extremely small size. Basically, the power we want to use. It's also one of the greatest problems we introduce into the situation. Also, there is the other situation that we are considering its state in a superposition, which is not discrete. So basically, what is the problem so far? Superposition, okay, small size, okay, yeah, sounds cool. So of course, it's not like that. We have several things there, which can completely, basically, disqualify the state of our computation in any of its phases. So the first thing is basically probably the most prominent nowadays for computers, and that is thermal noise. The thermal noise is literally temperature from the outside, which cannot fluctuate a lot, ideally not at all, and it's highly problematic already over 100 kelvins, which is not so much. Why? Temperature as high as 100 kelvins can already dramatically reduce spin lattice relaxation time, which subsequently reduces our spin relaxation time for the quantities T1 and T2. And the point is that this is the quantity which basically represents the coherency of the qubits. In other words, if we are getting around this temperature, then our computation is usually disqualified. Okay. Why the fluctuations? Yeah. Simply, we will cool it down or something. No, it's very fast. As just for imagination, on average, if you do not get to 100 kelvins, all the relaxation times are in the order of microseconds. Like, then of course there are other problems for macroscopic. One of them is huge, and that's the industrial noise. In other words, why do we don't have like the quantum computers inside of large cities? Yeah, why do you put it on some strange village or really on the suburb? Yeah, basically, this is the reason, and this is the reason we cannot avoid otherwise. Then we simply put the computers outside of the industrial parks. And of course, then we have one more prominent problem, and these are the cosmic rays. So, like, ideal place for the quantum computer, underground, no exaggeration. Yeah, all of these problems cause quantum decoherence. In other words, they simply interfere with our neatly prepared quantum states during the computation, and altogether, it's usually termed as a quantum noise. So now we have a look at the state of our initial circuits, just to monitor the situation. So we can see the state vector simulation where there are no shots, and it should be really precise. We can see 0101, and it is really precise. Okay. Now we can see like custom simulator result, which is already performing shots, but still with no noise involved. It is also precise, which is still expected. Here, we can see artificially edit depolarizing noise with the probability of 5%. And now, here we can see that definitely not all the shots went to the right state, but that we have some parasitic states around. The very similar situation, but more prominent as expected, is with the circuit representing our first excited state, where we do have most of the shots on the right states, but the polarizing noise already scatters some shots over another 8 states. Here we can see, just for comparison, 1000 fidelity, and we can see, not really here, but it's up to 1 first. So if we have no additional noise, the fidelity with the state vector is 1. Obviously, for the depolarization noise, it's not so good. So now, like, what will we do with that? Well, we will not only work with the depolarization noise, like the artificial noise model we just involved, but we will also try something on not for this presentation, not for real machines, but for mock backends provided by IBM, which basically provides us with a very accurate artificial model close to the noise on a real machine. Now, this was chosen purely from time reasons. So we had a look at Quito, Manila, and Nairobi computers. Why? All of them employ the Falcon processors, but of a different series. And of course, looking to write vastly different architectures. And we wanted to see the difference. So, the difference. If we have a look at the Hartree-Fock state now, or the Hartree-Fock circuit, let's call it, we can see that the cousin simulator with the 5% depolarizing noise is like kind of okay, not 100%, and that the Nairobi computer is even better in this case. Yeah, Nairobi is very, very stable, we can say. Quito and Manila are not so cool, and what's worse, they already exhibit kind of strong parasitic states. In other words, in this case, if we wouldn't know about our problem, of course, it's our initial circuit, but if we didn't, we could consider this to be simply a less probable state. This is something we should not tolerate in our computations at all. Similarly, here, where we can again see that, cousin with the depolarization noise is, and expected, Manila and Nairobi are really cool, and Quito is not. Now, at least from my experience, if you want to test something on a real computer which is really clean, then Nairobi is one way to go. If you want something on a more noisy machine, which wouldn't react as expected in many cases, then the great thing is Quito. That's why they were chosen in this case. And so basically, I said we shouldn't tolerate the stronger parasitic state like here. So what should we do with it? Well, we should try to correct them. And how? So let's look at the classical error correction, because we have errors even in a classical realm, in a macroscopic realm, when we are usually sending data over long distances and so on, and we do repair them. So maybe we should try that as an inspiration. Well, usually it's very straightforward. We have several encoding schemes. Here we have so-called repetition encoding, which is like the professional term for simply sending the same data multiple times. Yep. Okay, I have some low probability of mistake, so I will simply send it in a redundant manner. I will send it 2 times, 3 times, 20 times, and usually it will be more okay because it provides me with several informations. If not all the bits in the group are the same, then obviously there was some mistake. we have only 0 and 1 in the classical realm. Okay, so I have detection of mistake. Cool. If I have multiple or majority of the same values, and then there is like one different bit, then it's the faulty bit, certainly, if I'm not really unlucky. Yeah? So, okay, I have the correction. I can simply flip it at the recipient part. Not a problem. And then, of course, I can be a little more unlucky. There can be enough mistakes. And then, majority of the bits would be incorrect. Oh, no, it's the problem with the correction. But I can still at least detect that something was off. So probably it would need some other iteration of checking, probably with the sender. Okay. Okay. And what happens if all the bits are incorrect in a way that it is the correct message? Well, in that situation, we call it that we achieved the code distance or the encoding distance. And that's it. We have a term for it. In that case, we are completely unlucky. Our former information is lost, and we are not even unable to fix it. We are not even able to know about it or to recognize the mistake. Yeah, and that's the classical realm. It's not optimistic at all. And it's worse. Because now in a quantum realm, there are more problems. Yeah? Here, you have 0. You want redundancy, I simply copy 0, 0, 0 next to each other, a straightforward manner. Let's do it with a quantum state. Yep, 5 state, of course, I can clone it, or I can't. And that's it. Yeah, of course, here I can do some intermediate checking of the data. Yeah? I can simply read it one bit after another. Can I do it during my computations or something during the processing? No. If I perform the measurement, my wave function collapses. Okay, okay. So at least I can maybe work with the amount of mistakes. Yeah, like here. Here we can see how many mistakes can we repair because they are discrete. Yeah, 1 mistake for 3 redundant set. So 1 mistake is okay, 2 mistakes are too much for repair. Yeah, at least we can work with something like this. We cannot because we have the continuous superposition. We don't have any discrete mistakes in this manner. Okay, so basically, is this disqualifying for any correction codes? Well, it was believed to be until I believe in early 19th, where Peter Shor came for the rescue. And he showed us the way in which we can perform even detection and also the correction of mistakes. So now that's all, yeah? We will show that and it's done. No. Because in a classical realm, basically what we could see was a bit flip. We got incorrect 0 or incorrect 1. And our machine will get us 0 or 1, nothing else. Yeah. But of course, not even we do not have the discrete errors, as I've already said, but we do not have only bit flip errors. We do have bit flip errors, of course, we are not sure of them. And basically, the cool observation is that we can emulate them by applying Pauli X matrix to our computational basis. And then we have the facelet errors, which can be emulated by application of Pauli Z matrix. And that's it. It has no equivalent in classical realm. So, okay, that's another thing to consider. And it's still everything because, yes, this wouldn't be such a problem. Yeah, we have simply the state, we apply one or another, perfect well, we have one mistake, we do something with it. No. When we do have the computation, it is not performed completely immediately, and during the process, there is a lot of interaction with the environment. Again, we try to abstain of that, but it is there, and it further causes the incoherent evolution of our computational state. It continuously adds some incoherency to our situation. Okay, so basically, what do we want? Yeah, what do we want? Everything. Literally everywhere, every single step, there is some problem, and there is. So, what do we exactly want? We want to be able to detect the errors. Obviously, we want to be able, at least if anything else fails, we want to be able to say that the computation was wrong. Then we want to be able to correct the computation, obviously. Then we want to be able to basically prevent the error from propagating over the circuit, if possible, if that's even physically possible. And it is. Now, we can have a look here. And here we can see a very simple example of the circuit where we can emulate the error detection for the bit flip, only for the one most primitive pure mistake, no continuous incoherency, no other things, but this. Let's say we have a few qubits. Well, the first qubit is the original one we want to work with. There are the original data, the original state. Then there is the other qubit. What is this? Well, this one's purpose is the redundancy, as we cannot copy the quantum state, but we do not need it in this case, because the entanglement in some systematic way is enough. We introduce redundancy, or better said, we introduce extension of our Hilbert space, where the original data reside. And this was one of the ideas of Peter Shor, which is pure genius, because this can really emulate the copying of the data in a classical arena. And then we have the ancillary bit, which will basically decide about the mistake or not. Then this other block is the entanglement of the redundancy bits with the original data bits, let's say. And here, it will be the place for the mistake. I will get to that more in detail in a moment. And the rest of the blocks, yeah, here is the preparation of the ancillary qubit for the indication of a mistake. And this is, yeah, these two control Z gates are basically the pillar of the method, because this block, this set of gates, is called the stabilizer block. And basically this whole approach of quantum error corrections is called according to the measurement of the stabilizers or stabilizer measurement. And yeah, here is the measurement itself. So how does it work? Here we can see the 100 probability of measuring 0, which is okay. There are no mistakes. Literally, there is an empty block. Okay. And I've said we are detecting only a bit. Let's do the bit. We have one. We detected the bit flip. Okay. Okay. But that's on the data qubit. Yep. What if the bit flip happens on the redundancy qubit? Well, it's the same. We are equipped for that. And of course, now there is like a worst variant, or the worst case, where the bit flip can occur on both of them, because we do not abstain from that type of mistake. We do also have like the encoding distance here, and it can be achieved. In this case, very easy. We are okay. Everything is good. So, but we do not know about it. But yes, this is the simplest example for the bit flip detection. Now, like, yeah, what about the other things? Some correction, not such a problem. Now we have 5 qubits altogether. Yep. Again, we have some data qubits, we have some redundancy qubits, only 2 of them. It's cool. We have block with some error, and we have 2 ancilla qubits, and we have slightly larger stabilizer block. Yeah, nothing dramatic, 5 qubits. So let's have a look at it. No mistake, 0, 0. Cool, perfect. Bit flip on the first data qubit. 0, 1. Remember 0, 1. Okay. First redundancy qubit, 1, 1. And now we are there, because this allows us the correction. If we have only one of the qubits flipped. That's exactly the same principle as with the classical correction. This is the most probable type of error, because usually we don't have such an erroneous situations or such an erroneous environments. So if there is, in this case, only one qubit flipped, it's cool, we can detect its position and we can simply flip it back. Yes, of course, if we flip 2 of them, it's again the same situation as in classical. We do get some output and we see it's not 0, 0, but that's it. How do we now recognize it from the single bit flip on Q1? We don't. Okay, but still we could detect the mistake at least. Again, if we achieve the encoding distance, then it's completely lost. This is something we do not want to have. Okay. And now I'm aware of talking about the face flip and everything. So what about the face flip? Is it possible also to do with some stabilizer? Yes. Now we have 6 qubits, and this is our whole circuit. It's more robust with respect to number of qubits, and it's even deeper, significantly deeper. And emphasizing this is only a detection. We just put there one more feature that now we cannot correct, but we can detect and differentiate between 2 types of the error instead of 1. Okay. Again, these are the initialized data. This is the entanglement with the redundancy qubits. This is the error preparation of ancilla qubits. And now we have 2 stabilizer blocks instead of 1. Before we had to control these, and that could detect the bit flip. Now we also have C nodes, and we can deal with the detection of face flip. So let's have a look. First of all, 0, 0. No problem, literally. Bit flip. 0, 1. Cool. Let's put it somewhere else, just to see if it doesn't surprise us, and it doesn't, obviously. We are able to detect that it is a bit flip. That's all the information we get. Okay. Let's put a face flip somewhere. 1, 0. Yeah, we are detecting a face flip. Okay. No other information. We do not know the affected qubit, but we know about the type of the error. We put both of them together, 1, 1. We are also able to detect that. Cool. And that's it. Again, we can put there more problems where we do simply blur our vision of the error so that we aren't able to tell exactly what error is there or how many times it is there, but we at least see that the state was somehow compromised. Okay. Yeah, like this. Okay, and now basically this is okay. Yeah? We've solved the situation. We're going to get a copy. Quantum correction. Unfortunately, it's not so easy. Well, it would be really cool. The point is, can we do the correction here? Yes, we can. With a larger circuit. Much larger, but we can do the correction and the detection, everything together. The principle works. But the problem is, we are much simplifying the situation. So far, I've emphasized, we had the block to generate the state. We had the block to entangle it with the redundancy qubits. We had another block to generate the error. Okay? But is it like that in reality? Is our problem literally in one faulty block? No, not at all. The errors are not localized in the real computer. And the errors are not even being created on the inside of the computer, as we are talking about the incoherency caused by the interactions with the outside environment. So the error can be there any single time, and it will. Okay. Also, because of the incoherent evolution, even the errors are not really coherent. And they are still not the same. So, okay. Like, can this be improved on somehow? Yes. Basically, based on the work of Peter Shor, we can deal even with situations like this. And it's even better because we have the theory which allows us to basically guarantee that the errors will be mitigated to keep them up to an arbitrary degree, which is really cool. That's a very strong result. So what's the problem? Well, the problem is that we need, for some practical applications, it's usually set at least over 1,000 qubits. For general applications, probably much more. And we are not here yet, as our next future milestone will be NISQ machines, which basically we like to categorize as being from 50 to several hundreds of qubits, so that we do not reach even like the lowest level of fault tolerance, not even theoretically. And we do not get the general quantum supremacy either. So, come on. Okay, now basically, now we are done. Yeah? We can go for a coffee. Simply nothing can be done. Basically, it's all on the paper. We should all do the integrals and inner products. Nothing works. Well, it's not so bad. At first, we have our VQE. We have our quantum neural networks, which can be trained up to some degree, even some practical degree, even now. And with these machines, it will be even better. So maybe it will be just like kind of a game or very, very specific accelerator, something like GPU, but much more narrow profile thing, maybe. Hopefully not. And yeah, no Shor's algorithm, which is kind of unfair considering he did such a job on that so far. But yeah, is this all? No, not even close, because we have something else, which basically takes a lot of different approaches and basically tries to fight back as, okay, there are people working on larger and larger computers, which will be necessary and maybe fault tolerant by themselves one day. That's cool. Until then, we can simply fight the noise. We can either try to prevent it or we can try to remove it ex post. Can we? Yes. And that's what we call, in the slangish way, noise mitigation. Now, methods of noise mitigation are not a homogeneous group, not at all. Some of them, like for example, software method, is something very close to the original quantum error correction, as we will see. Then something like zero noise extrapolation on the other hand, basically takes a lot of results and tries to literally compute the right result out of them, trying to somehow systematize the errors. And then there is the measurement error mitigation, which uses very, very simplistic approximation, which ironically works extremely well on our current circuits, as we will see, and I will tell why. And there are many other methods which we are not talking about today, but I chose these three to showcase that they are all basically the representatives of completely different family of the methods. So zero noise extrapolation does not require additional qubits, which is cool. And we will see that it requires something else, but it does not require larger computer. Here, the point is that basically, yeah, we cannot just say, okay, now you will step down with the noise by 20%. Not yet, at least. But we can somehow quantify how much, with respect to something else, we will increase the noise. Yeah, now I'm talking probably too long and I got completely carried away, yeah? Increase the noise. No. The point is that we can scale the noise, as we call it, in several ways. The most prominent ones are unitary folding because of its simplicity, or pulse stretching. And then we can somehow extrapolate from these results. So unitary folding is very simple. Basically, we are using this identity that, yep, unitary operator with it multiplied with its Hermitian conjugate is the unitary operator or unity operator. And now we simply either take our whole circuit, we call it global unitary folding, and we simply put it like into the larger circuit, multiply by something else. Cool. And we have second level folding. If we did it again, we have third level folding and so on. We can also do this very same principle with the separate gates. We can also multiply it from the right side, from the left side, or completely in a random way. Everything is used, and sometimes it works better than the other way around. And the most important thing is that I know what I have done and how many times, and I will get some result corresponding to my quantified modification. But I know literally I did like 2 times the folding and I got this mistake. I did it 4 times, I got this mistake. Now we are not getting completely something random, which we cannot take into our hand. Now we have at least some correspondence. The similar approach aiming to achieve the very same thing is being used on computers which utilize pulse level control, where we can simply aim for longer pulses, which do provide more time for some errors to happen. And of course, we know exactly the time length of the pulse. After this, we can very simply approximate the expectation value by extrapolation from, or the ideal noiseless expectation value, by the extrapolation basically from the other end. We see worse and worse errors, and we will try to describe the trend with some very simple function. It can be exponential function, it can be some polynomial, even linear function is sometimes used. And we will extrapolate to the noiseless limit and hope for the best. If the interpolation and the extrapolation parts are okay, we are cool. So is this like the ideal situation? Yeah, is this the like the holy grail? Maybe it is, and it's basically the state of the art. But the point is, we need a lot of these expectation values, which is cool if we have like one circuit or something, but it's extremely prohibitive with respect to the real runtime in iterative methods, like VQE, for example. Oh, yes, this is what I said. We can see some results. So we have, again, the hard Fock circuit with the state vector. Again, depolarizing nodes on a cousin simulator. And then here we take just like the best and the worst machines from our set. In other words, Keto and Nairobi. Both are cool after mitigation. Both are improved, albeit maybe not by much, but they are. But have a look here. Nairobi is basically the same and improved on both states of the superposition. Keto is worsened by this. Okay, what does it want? Well, more expectation values and different extrapolation. And now this is the problem because we need to tune it for our situation. We aren't in the phase, and maybe we won't be with this approach in the phase where we have some general formula, which we simply apply and it works completely well. No, not all. The other method is the software mitigating method, which is kind of more technical. We have our circuit and our virtual qubits in the circuit. And now we have physical qubits in our computer, which are basically assembled in some way, in very different ways, as we've already seen. And now we need to basically take some indicator mistake. Typically, it's a readout error. So, in other words, the error of a measurement, or the errors on the rotation, on general rotation of block sphere, on the U3 gates. And in this case, we want to simply list or do order the physical qubits according to their capability to deal with the specific mistake and to somehow, yeah, and we will simply assign our virtual qubits to the best ones. Sounds cool. Okay, so the Hartree-Fock initial state. Yeah, we have the state vector, we have the Keto, and we have Nairobi. Keto is improved, really improved. Nairobi is worsened. How's that possible? Now here, Nairobi is worsened, Nairobi is improved, and Keto is completely killed. But it's completely killed. Yep, we should have saved our time. Like, what happened here? Well, the situation is that this is basically the worst method to be used just heuristically. We need to know our architecture very well for that. And sometimes we are simply unlucky, especially if we have smaller computers which have like 4 or 5 qubits, because we will basically reorder the virtual qubits. The improvement is very insignificant, and we could introduce, by pure bad luck, enhancement of the other mistakes, which happened here, obviously. Well, and the last measurement, error mitigation, is something we were already mentioning. And this is, let's say, exposed technique. This one does not aim to prevent the error like the previous one, but it's more closer to zero noise extrapolation. We want to somehow post-process our result to get the real cool results. So what is here? We simply think in an extremely simplistic way that we introduce the approximation where all the circuits, we are real optimists, all the circuits is okay, and the error is right at the end during the measurement. Cool. And so it means that we are basically obtaining some noisy vector, but this vector is basically the ideal one, the perfect one, just multiplied by something, by some transformation, by some matrix. Okay, so what we can do? We can do the transformation matrix from the states we know, where we are able to quantify like the probabilities, which means the basic states. So we perform the measurements on basic states, we get the probabilities and the matrix, we make its inverse, and we multiply our noisy result. That's extremely cool. Let's have a look here. So measurement error mitigation, again, polarizing noise, there it is perfect, basically it's perfect. Especially on our hard Fox circuit, and that's something I'm going to back around in a few seconds. On Quito it's improving, on Nairobi it's improving. Okay. Here again, it's improving. So now we found the overhead, finally. Yeah, it took like 45 minutes. Yep. So basically, is it that? Well, partially. Now, while the measurement error mitigation is something which is extremely cool because it is simple and the measurements are mostly done, or the overhead is mostly done in the preparation phase with the basis states and the inverse of the matrix, which in a classical HPC always used to be like a really huge overhead, but considering our situation, it's completely cool. So it is completely nice. This, well, it is working extremely well, even with the approximation. And why? Because our tested circuits are really shallow. In other words, the error is really almost at the measurement. It's very close. If we had more, or we had deeper circuits, the results will be much worse. Okay, and there is also another positive point, and that it can be generalized. Usually, if we do it on our machine, we assume basically that the errors will be very much the same on the other circuits, which do not have to be, but they will be similar. So just the final summary. We have the quantum error correction, something which is almost perfect, and it's exactly what we want. But in general, the qubit registers will be really huge, and the circuits will be really deep for general solution. Considering zero-noise extrapolation, it introduces a huge overheads, and the extrapolation doesn't have to be precise and doesn't have to be even sufficient. Considering the software method, we need to know our hardware, which is not so like difficult. Of course, we can simply read about it. We can see it online on pages of IBM, but it's not always sufficient, and definitely it's not general. We need to tune it for our needs very carefully. And the measurement error mitigation, yes, it's hands down the best for very shallow circuits. Otherwise, it's not. So basically, my last point, and the rest is for another presentation. So basically, what now? Like, are we simply, or do we simply have to just wait for maybe better machines and that's it, and be passive? Something that wants something relatable now. Basically, well, you are in the middle of a zombie apocalypse. Yeah. And now it is like, okay, basically I can just, maybe the final solution is to kill the alpha zombie, to shut it in the head somewhere, or maybe to create a vaccine, maybe just to simply wait up to the end of the 10th season on Netflix. Yeah, maybe. But before that, I need to survive. And for that, we, at least with respect to the iterative methods, we have some noise resilient optimizations, which work with a different degree of success, and we will let it for next time. Thank you very much. Of course.
So have you gone and read like the plots that you showed?
You mean this one, or? Yeah, I don't have them here, but we can definitely have a look at it after, like, after a session or something.
Okay.
It wouldn't be at worst tomorrow. It wouldn't be like a problem to combine them. Basically, what I was aiming to do and why I ordered it like this was that zero noise extrapolation is like a hot topic nowadays, especially in IBM. So I wanted to show that as like the first thing, basically as the like hot state of the art, and then tell its disadvantages, basically then come slightly back to something which is more resilient and more reliable.
And the question about the unitary folding that you mentioned,
yeah.
You said you can do it globally, locally, and then you said, well, sometimes one works, the other one. Versus local.
Well, I have heuristic, but I don't have the rule for the comparison or something like that. But or I don't have any justification yet, at least. In time, either me or somebody will have to have some, but we don't. So from my simply empirical knowledge, the best is usually not to be focused on the extension on one side, but hands down the best approach is usually to use the local one and to have a completely random site of the folds, we can say. So yes, the heuristics or maybe the algorithm will be definitely in this direction, but I have no rule for it. Honestly, I use it exactly in a random manner.
And check the third question. When we looked at this problem for the type of system we cared about, we did the models. We used the error models. Then we went to the devices and we discovered there was almost a connection. Have you tried the devices?
Yeah. I will show you two plots from the end which you wouldn't otherwise see. Yeah? Here we are doing around these packets. And yes, basically here we have the state vectors and the depolarized vectors. Yeah, bad convergence because these are local, old school, no noise resistant methods, which I hoped for basically. Here we have immediate filtering and snop fit. Yeah, more modern methods. Snop fit disappointed me in this one point. Otherwise, it's smoother, it converges better. Basically, it seems just like a systematic shift error. That's cool. And this is still depolarizing noise. We strengthened it, 2%, 5%, still smooth. Yes, the systematic error worsens, the shape of the curve worsens, but it's still okay. And then we go to Nairobi, which was cleaner with respect to the shots in the initial circuit, emphasizing the initial circuits, both of them, which you remember very probably. And here is the result of the two noise resilient methods without further tweaking. I used just the default settings from Qiskit simply to try it from the point of like complete user, which are basically jam with respect to these methods. So yes. So basically, judging just from this few data we have, the connection could be that the less noise is in the initial circuits, the worse will be the result of the iterative method. But yes, you are right.
Any other question from the audience? Nothing. I have a question concerning the presentation of the stabilizer parts. I would like to know actually how is the scaling of this additional part of the circuit you have like to put at the end of the circuit. For me, it seems to be more or less linear with the number of gates you have to add, but is it like true or not? Maybe you got some insight.
Yeah, basically it's not completely linear. It's worse somewhat because there have to be more and more redundancy qubits, which are not only entangled. You have to put some basically some Hadamard gates into that and so on to, let's say, extend the Hilbert space in a systematic but more complex way than just add one qubit after another and just put another C node in it. And then it requires like slightly more complex controlling between the ancilla qubits and the redundancy qubits in this case.
Okay.
Unfortunately, I don't have any other interactive example for like larger circuits where it would be more visible.
Okay, we'll discuss about that together.
Yeah.
Nice. Okay, well, I guess that if there is no question from the audience or on Zoom, we're going to stop here. Thanks again for your very nice and pedagogical talk on the noisy parts of quantum computing. We learned a lot, I guess. And it's time for a coffee break now.